Hey guys, welcome to day 9. Today we're looking at a massive topic in AP Calc. This will be our focus for the first half of the year. Will be on the derivative. Okay, a couple of things about the derivative. Let's relate it back to something we know, right? Slope. So if I have a line, this is the point x1, y1, x2, y2. We can calculate the slope of that line by doing the change in y over the change in x. Okay, and we've done that, you've hopefully done that since 8th grade, 7th grade, 8th grade, 9th grade for sure. So we can always calculate slope of a line as long as we have 2 points. We can just do change in y over change in x. But what calculus is going to deal with is, what if we have a curve? What if we want to find the slope of something that has a curve? So let's just sketch a little parabola in here. What would be the slope of this curve? Well, it's not the same as a line, right? And you can think of it as, well, at this point right here, that point right there, it appears that we have a negative slope. At this point on the right here, it looks like we have a positive slope. This point right here, it looks like our slope is 0. The idea here is the slope is changing, right? We have different slopes at different places. And we can, what we're going to do in calculus is we're going to sketch a tangent line. You should know that from your geometry class with either me or Ms. Stevens or Mr. Lux. A tangent line, this right here is a tangent line. We know that a tangent line, we talked about it in terms of circles. A tangent line touched a circle exactly once. Well, a tangent line touches a curve exactly once in just a little range of an area. So if we could figure out the slope of the tangent line, that gives us an idea of what the slope of the curve is at that exact point. So what we'll be doing a lot of this for the next foreseeable future here is finding the slopes of these tangent lines. And that's called the derivative. So the derivative, this is also called slope of the tangent line. We also call the derivative an instantaneous rate of change. We've always referred to slope as a rate of change. However, in this linear function, the rate of change is the same consistently across the entire line. With the blue parabola there, the rate of change is different depending on which x value we look at. So we talk about an instantaneous rate of change, the rate of change at that instant for that very particular x value. Whereas on a linear function, the rate of change or the slope is the same everywhere. Okay, so how do we then come up with an idea of the slope of this tangent line? That's what a derivative is. It's the slope of a tangent line. So let's take a look at a curved function. Let's try that again. Okay, so here's our y, here's our x-axis. And whatever color this is my function f of x that's curved. what I want to do is I want to figure out the slope of the tangent line for some point that I'm just going to call x. Okay, so I'm going to place x right here. So I'm going to refer to this point as, this point right here is the point x comma f of x. Okay. So all I have to do is find the slope of this tangent line that's tangent to the graph at the point x comma f of x. I'm going to sketch in this tangent line. So this blue right here, this blue line is the tangent line. And my goal is I want to find the slope of that line. Now, depending on where I place x, it's going to have a different slope. Right? If I moved x a little bit closer to the origin, my slope would be a little bit less steep. If I moved x away from the origin a little bit more, my tangent line slope is going to be a little bit steeper. But again, I'm just, for a general, any value x here. Okay. The question is, how do I find the slope of this line when I only know one point on the line? The only point I know is the point x comma f of x. How am I supposed to do change of y over change of x when I don't have another x and y on this line? Okay. Well, the answer to that question goes back to our good pal, limits. So here's what I'm going to do. I'm going to go back to what I know. I know how to find slope when I have 2 points. So I'm going to choose another point that is on my function f of x, I think it's red line. So I'm going to choose another point on here. Okay? And what I'm going to say is this point now, this distance right here is a distance h away from x. I'm just going to call this distance h. Maybe h is 1, maybe h is 0.5. Whatever, that distance is h. Therefore, my new x value here is x plus h, with a new y value of f of x plus h. So what I'm going to do now is I'm going to connect that x plus h comma f of x plus h. Yeah, just drawing to this point, it's the point x plus h comma f of x plus h. You may say, what the heck is h? It's just that arbitrary distance that I put between x and the other point that I wanted. So what I'm going to do now is connect the two red dots here. And I'll connect them with a different color. I'll use green. Now this line this new green line is not a tangent line because it touches this curve twice. Do you remember the word from geometry for a line that touched a circle twice? That's right, it's called the secant line. Now, we can obviously tell that the secant line slope is not the same as the tangent line slope. The green line slope is different than the blue line slope. But we can also tell that they're pretty close. If I wanted to write a formula then for the secant line slope, so this slope right here would be equal to the change in y. Well, that would be f of x plus h. Okay. This is like y2. This is like y1. So minus f of x, change in y, over the change in x. Well, that'll be x plus h minus x. Now, to see how this simplifies then, we can't simplify the top. But that bottom, I have an x plus h minus x. Those two, that x and that minus x are going to cancel. And I'm going to be left with f of x plus h minus f of x over h. And that is the slope of my secant line. Now again, you may say, well, who cares? It's not the slope of the tangent line. But what if I made h a little bit smaller? Okay, the picture's going to get, you don't need to keep adding these into your picture. Okay, it's already pretty convoluted here. But imagine if I let h be a little bit smaller. We'll use a black line for that. If I made this h smaller and put it right here, now the slope of this line, now my secant line slope still doesn't match my tangent line slope, but it's a lot closer. Well, what if I made h even smaller? What if I made h really, 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 really small? And I put those 2 points almost right on top of each other. If I did that, I'm going to get a really, really good, in fact, I'm going to get a perfect approximation for my tangent line slope. Well, how in calculus have we shrink things down to 0, right? We use limits. So here's where the limit definition comes in. I'm going to use this slope, but I'm going to shrink the distance between those points down to 0. So first off, derivative notation right here. F prime of x. F prime of x means the derivative of f of x. That's our derivative notation. Well, the definition of a derivative then is we do the limit as h at distance between those 2 points. We're letting the limit of h go to 0 of f of x plus h minus f of x over h. Now, we can see here, well, what's going to happen if we plug in 0 for h? Well, then we get f of x minus f of x, which has to be 0, over h, which is 0. We get 0 over 0. Now, with functions, that means the function's undefined. But limits can handle 0 over 0. Okay? And again, this f of x plus h minus f of x over h, this is coming simply from the slope of the secant line. That's where we get that. But shrinking h to 0, letting the limit as h go to 0, gives us the slope of the tangent line. Okay. So executing this limit will give us a function for the derivative of f. And then we can plug into that function and find the instantaneous rate of change, right, or the slope of the tangent line at any point on a curved function that we have. That's what we'll be looking at tomorrow in class. So get ready, and I'll see you guys then. Talk to you later. Bye.